Today we're going to be talking about earthquakes and logarithms. So in the 1930s, Charles Richter developed this Richter scale, which gives us a mathematical model for the magnitude of an earthquake in terms of this ratio between the amplitude of the earthquake wave, which is usually measured by a seismograph, and we call it the intensity of the earthquake, compared to that amplitude of the smallest detectable wave, which we'll denote by S. Okay, so the formula that actually ties these together is this R equals the logarithm of A divided by S, where this log is dealing with the base 10 since it's one of the common logarithms. The beauty in this is actually when you're looking at those values for the earthquake, the Richter scale, so far we've had earthquakes between 0 and 10 on the Richter scale, whereas the intensity can be numbers ranging from around, so the smallest detectable wave is this movement of 10 to the negative 4 centimeters or 1 micron to something as large, I mean, it's 800 million times as intense as that sort of measurement. So you really have this wide range of values, and the Richter scale kind of brings that down by using the logarithms. So we can actually get some good measurements going on here. And so for this problem, what we want to look at is Chile's recorded two of those largest earthquakes, one in 1960, another one in 2010. And the 2010 earthquake actually registered a reading of 8.8 on the Richter scale. And so this 1960 earthquake, in comparison, was 5 times as intense as that 2010 earthquake. Can we determine the magnitude of that 1960 earthquake in Chile? And the answer is yes. And in order for us to do that, we're going to need to do a little bit of work. And the first bit of work is we're going to need some labels on things. Since we have 2 different years, we want to look at 2 different magnitudes, and we'll label them as such. So the first one that we'll label is we'll use this R with a subscript of 1960, and that's going to denote the magnitude of our 1960 earthquake. Okay? And then R of 2010, we're going to use that as the magnitude of the 2010 earthquake. So hopefully there should be no surprises going on right there. Now, with that in mind, we actually do have a relationship that we have. First off, we have the R 2010. If you take a look, there's another way we can write it, and it's simply 8.8, because if you look in our reading right here, we have 8.8 on the Richter scale. So this deals with that 2010 earthquake, so we'll just write that as 8.8. And then moving forward from there, we also know from our formula, this R equals log of A over S, that we can write R of 2010 as this log of A of 2010 over S, where A of 2010 just happens to be the amplitude of that 2010 earthquake. So now we're in a good position to also write the amplitude of the 1960 earthquake. That's just going to be A of 1960. So the amplitudes of those waves, we have those labeled. So now we have the relationships. What are we actually looking for? And what we're actually looking for here is just our R of 1960. And the way we can do that, we can use our formula once again. That's just a log of this amplitude of the 1960 earthquake wave divided by S, where S is that standard that we've talked about before. So moving forward from there, where can we go? Well, if you look in the problem, we have that this A of 1960, there's another way to write it. And if you read it, you see the 1960 earthquake was 5 times as intense as the 2010 earthquake. So that means that A of 1960 equals 5 times that A of 2010. So that means we can rewrite this logarithm as the log of, instead of A of 1960, we now have A of 2010 times that 5 out in front. Okay, and all that's divided by S once again. But this is a nice simple format. And the reason why happens to be, if you take a look at this problem, there's actually some beautiful properties of logarithms, and they're called the law of logarithms. In particular, there's a product rule of logarithms. And so what does the product rule of logarithms state? It says if you have a log with some base, we'll call the base b in general, of x times y, that's the same thing as the log base b of x plus the log base b of y. Okay, so that allows us to actually rewrite this thing, our log of 5 times a of 2010 divided by s. That's the same thing as log of 5 plus the log of a of 2010 divided by s. That's just using the product rule. So that law of logarithms comes to our rescue here. And now we can use that formula we had before. We had r 2010 equals that log of a of 2010 divided by s, because that's our last term. And so we know the log of 5. We can figure that out just by punching it into the calculator. You'll get this 0.69 such and such number, and we can round that just to 0.7. That's usually where our Richter scale measurements are going, to the tenths. So we have the 0.7 for the log of 5, and then for the log of a of 2010 divided by s, if you just look, that's the 8.8 because we know that our 2010 equals 8.8. So we can write this as 0.7 plus our 8.8, and that all of a sudden equals 9.5. So now we have a solution, and all we had to do was use this product rule logarithms, and so we didn't need actual values for our amplitudes or for our standard wave. We can avoid that just by using the law of logarithms, right? And in particular, the product rule.